Welcome to part 2, S-curves. In this video, we're going to cover a class of functions that are shaped like an S and have asymptotes at both ends. So one of these functions is called the logistic function and has this particular formulation over here, 1 over 1 plus e to the x. Let's go ahead and plot this to see what it looks like. So as you can see, we have a simple S-curve that has asymptotes at 1 on the left side and 0 on the right side. So what we're looking to do right now is to build a curve that's going to match the coronavirus case curve, or the cumulative coronavirus case curve, and those start at 0 and work their way up to some sort of asymptote on the right. So this is the correct shape, but it needs to be rotated around the y-axis because we don't start at up. We don't start at some positive cases and go down to 0. It's the other way around. So the way to do this algebraically is simply to multiply x by -1, and that's what we do over here. So our new formulation is 1 over 1 plus e to the negative x. So it's just symmetrical around the y-axis. We just flip it around. So we're beginning now at 0 and ending at 1. So while this is, now we have it in the right direction. Coronavirus cases don't just asymptote at 1. And what we'll do is we will scale this graph up by multiplying it by the numerator by some value. So we're going to introduce a new parameter here called L. And the formula here is right here. L over 1 plus e to the negative x. So whatever value of L is, it's just going to scale the graph up by that number. So we're just multiplying the whole function value by L, essentially. So before it was just 1. Now we're making it 10,000. So the graph looks exactly the same, as you can see. The only difference is the y values. This will allow us to scale it up so that we can match it to any coronavirus case number, regardless of how high it is. Okay, so this looks good. We still have some issues here, is that we have negative values for x. So here x is the number of days that have transpired, and we can't have negative values. So we need to shift the data, the curve, to the right. And the way to shift this is with adding a new term. And this is just a common algebraic maneuvering, is to subtract x by some other parameter here. We're just going to call it x naught. So this x naught also functions as what's called the midpoint or the inflection point. So if we look over here at 0, we have that the y value is directly in the center between the left and right asymptotes. So this will always be the case, is that there is some middle point, and that will by default be at 0, and it will occur right between the left and right asymptotes. Now if we move it to x naught, which we do over here, we're going to move the function to the right 50 days, and we're actually going to, instead of going from -5 to 5, we've gone from 40 to 60. So now our midpoint is at 50. It's also called the inflection point because this is the part of the graph where instead of we have exponential growth here, it actually turns from exponential growth to exponential decline. It's right at that point. So that is also known as the inflection point. So here, what we've done is we've continued to set L at 10,000. So that will be the asymptote on the right side. Our midpoint will be 50. That essentially shifts the graph to the right 50. And then we'll just plot the same graph. Now, you'll notice that it looks steeper, and it just looks steeper because the graph covers 20 units of x instead of just 10 over here. So that's why it appears steeper, but the steepness is actually the exact same. So our curve is looking better. We can use just positive values for the x. The y we can scale up to any amount. The issue remains is that our steepness we cannot change with this formulation. So we need to add a new parameter here, and this is another just common algebraic transformation maneuver, which is just to multiply x by some number. If it's a fraction, like less than 1, then it will flatten the curve. If it's greater than 1, then it will make it even steeper. So we just added a new parameter here, k. And in this instance, we're going to make k equal to 0.1, which will make it quite a bit flatter. We're actually going to make our x go from 0 to 100 instead of just 40 to 60. So here we have flattened it out significantly over a much greater period of x, and we can control the height with L. So k, again, is our growth rate. That's what controls the steepness. And then x naught controls where the midpoint is. So we have these three parameters that we're going to use for this logistic function in order to make this curve match the coronavirus case waves that we've seen with our actual data. So that's a brief introduction to the S-curves and the three main parameters that come with this simple logistic function.